Heat transfer enhancement in heat exchangers using customized turbulators. Abstract heat transfer augmentation techniques are used to increase rate of heat transfer without affecting much the overall performance of the system. Heat transfer augmentation techniques are commonly used in areas such as heating and cooling in evaporation, air, conditioning equipment, thermal power plants, space vehicle, automobile, etc. Heat transfer enhancement by creating turbulence in the physical behavior of fluid flow inside the heat exchanger tube has become a really interesting area for the researchers in order to reduce the size and cost of the involving equipment, especially in heat exchangers. This project report represents the effect of the Conical circular ring, CCR, on the heat transfer and fluid friction characteristics in a heat exchanger tube. The numerical analysis were conducted in CFD with NCCRs of various geometries, including 3 different diameter ratios, dr equals d/d equals 0.6, 0.7, and 0.8. Hot air is passing in tube under constant heat flux condition in the present work. The Reynolds number was varied from 8,000 to 18,000. Keywords: heat transfer, Reynolds number, thermal enhancement factor, customized turbulators. Introduction. Heat exchangers are used in different processes ranging from conversion, utilization and recovery of thermal energy in various industrial, commercial and domestic applications. Some common examples include steam generation and condensation in power and cogeneration plants, sensible heating and cooling in thermal processing of chemical, pharmaceutical and agricultural products, fluid heating in manufacturing and waste heat recovery, etc. Increase in heat exchangers' performance can lead to more economical design of heat exchanger, which can help to make energy, material and cost savings related to a heat exchange process. The need to increase the thermal performance of heat exchangers, thereby affecting energy, material and cost savings, have led to development and use of many techniques termed as heat transfer augmentation. These techniques are also referred as heat transfer enhancement or intensification. Augmentation techniques increase convective heat transfer by reducing the thermal resistance in a heat exchanger. Use of heat transfer enhancement techniques lead to increase in heat transfer coefficient but at the cost of increase in pressure drop. 2. Classification of enhancement techniques. 1. Passive techniques. 1.1 Extended surfaces. 1.2 Displaced enhancement surfaces. 1.3 Swirl flow devices. 1.4 Coiled tubes. These techniques generally use surface or geometrical modifications to the flow channel by incorporating inserts or additional devices. They promote higher heat transfer coefficients by disturbing or altering the existing flow behavior, except for extended surfaces, which also leads to increase in the pressure drop. In case of extended surfaces, effective heat transfer area on the side of the extended surface is increased. 2. Active techniques. 2.1 Mechanical aids. 2.2 Surface vibration techniques. 2.3 Fluid vibration. 2.4 Electrostatic fields. These techniques are more complex from the use and design point of view, as the method requires some external power input to cause the desired flow modification and improvement in the rate of heat transfer. 3. Compound techniques. 3.1 Rough tube wall with twisted tape. 3.2 Rough cylinder with acoustic vibrations. 3.3 Internally fin tube with twisted tape insert. 3.4 Fin tube with fluidized beds. A compound method is a hybrid method in which both active and passive methods are used in combination. 2 or more techniques may be utilized simultaneously to produce an enhancement. 3. Experimental setup and calculation. The details of the experimental facility are demonstrated in Fig. 1. The apparatus consists of 0.5 HP suction type blower, an orifice flow meter, a heat exchanger tube, test section, a U-tube manometer, a micromanometer, a set of temperature measurement devices, thermocouple, a variance transformer, a watt meter, nichrome wire for heating the test section with asbestos coating for insulation purpose. The tube is made from mild steel because of its high thermal conductivity. For heating the test section and to provide a uniform heat flux boundary condition, a continually wound flexible electrical wire is provided. It is a nichrome wire, provided with asbestos coating of thickness 5 cm as an insulation to minimize the convective heat loss to the surroundings. 1 Components. 1.1 Bell mouth inlet. 1.2 Calming section. 1.3 Test section. 1.4 Thermocouples. 1.5 Watt meter. 1.6 U-tube manometer and micromanometer. 2 Working. The air is sucked in a calming section with a bell mouth inlet by a blower with capacity 0.5 HP. After the air is fully developed in the calming section, it enters the test section. The test section is provided with the circumferential heater along its length. The thermocouples are provided on the test section to measure the temperature of the heated air. Due to the circumferential heater, only the layer of air in contact with the inner diameter of the pipe gets heated up and the air at the center is slightly heated up. To avoid such condition at outlet, to get correct reading, baffles are inserted at the outlet of the pipe to maintain the uniform temperature of air by thoroughly mixing it after outlet so as to get the correct output temperature reading. The pressure drop across the tube is calculated with the help of the U-tube manometer. For the Reynolds number ranging from 8,000 to 18,000, the heat transfer and the friction factor is calculated for the plain tube as well as for the inserts with 0.7 dr, 0.8 dr and 0.6 dr blockage area. 3. Pre and post experimental data reduction. 3.1 Reynolds number, Re. 3.2 Wall surface temperature, TW. 3.3 Bulk mean temperature, TBM. 3.4 Nusselt number. 3.5 Friction factor. 3.6 Thermal performance factor, DOT. These are the calculations need to perform before conduction the experiment. Reynolds number is a parameter which indicates the flow regime of the working fluid and defines as Reynolds number, Re, equals, V * D, / where, equals kinetic viscosity of working fluid, M2/S. D equals diameter of pipe, M. V equals flow velocity, M/S. It is the average inner wall surface temperature measured by 10 thermocouples. It is calculated by taking average of 10 thermocouple temperature readings T2 to T11. TW equals T2 plus T11/10. It is also called average bulk temperature. It is a convenient reference point for evaluating properties related to convective heat transfer. TBM equals tin plus tout/2. Where A equals heat transfer area equals inner surface area of pipe, mm2. TW equals average inner surface temperature of test tube, 0C. TBM equals bulk temperature of air, 0C. Tin equals inlet air temperature equals T1, 0C. Tout equals outlet inlet temperature equals T13, 0C. CP equals specific heat of air at TBM, kJ/kgk. Equals mass flow rate of air, kg/s. The Nusselt number is a measure of the convective heat transfer occurring at the surface and is defined as Nusselt number, nu, equals, H*D/K. Where H equals convective heat transfer coefficient, with M2K. D equals diameter of the tube, M. K equals thermal conductivity, with Mk. Friction factor, a dimensionless parameter F is written as friction factor, F, equals .P/L/D, 1/2 *V2. Where, .P equals pressure across test section, Pa. It is defined as the ratio of the heat transfer enhancement ratio to the friction factor ratio. TPF, dot. Equals, nut plus nup, /foot/FP, 1/3. Where nut equals Nusselt number for pipe fitted with turbulator rings. Foot equals friction factor for pipe fitted with turbulator rings. Nup equals Nusselt number for plain or smooth pipe. FP equals friction factor for plain or smooth pipe. 4. Method of determining solutions to flow problems. Computational fluid dynamics. Computational fluid dynamics, CFD, is the use of computer-based simulation to analyze systems involving fluid flow, heat transfer and associated phenomena such as chemical reaction. A numerical model is first constructed using a set of mathematical equations that describe the flow. These equations are then solved using a computer program in order to obtain the flow variables throughout the flow domain. CFD procedure followed. Preprocessor. Preprocessing is the input of a flow problem to a CFD program by means of an operator-friendly interface and the subsequent transformation of this input into a form suitable for use by the solver. The steps involved in this are 1. Definition of geometry. 2. Grid generation. 3. Selection of the phenomena or system to be modeled. 4. Definition of fluid properties. 5. Boundary conditions specification. Solver. 1. Approximation of the unknown flow variables by means of simple functions. 2. Discretization by substitution of the approximations into the governing flow equations. 3. Solution of algebraic equations. Post-processor. All the leading CFD packages are equipped with versatile data visualization tools. These include 1 domain geometry and grid display. 2 vector plots. 3 line and shaded contour plots. 4 color PostScript output. The mathematical modeling of a flow problem is achieved basically through 3 steps. 1. Developing the governing equations describing the flow. 2. Discretization of the governing equations. 3. Solve the resulting numerical equations. Governing equations. V. Numerical investigation for plain tube and with insert. The numerical analysis is of air flowing through a horizontal circular pipe at constant wall temperature, for estimation of the heat transfer and friction factor characteristics. The results obtained from numerical investigations are validated by comparing with the available correlations. 1. Plain pipe. Consider the problem of air flowing through a circular pipe with length, L, and inside diameter of 1800 mm and 48.5 mm respectively. 2. Pipe with ring inserts. The inlet and outlet diameter of the pipe with the circular rings inserts and with diameter ratio of 0.6, 0.7 and 0.8 dr is given in the following table. The rings are inserted in the test section of the pipe. The length of the test section is 1000 mm, so there are 20 rings in total, with the first ring placed at 39.25 mm from the comming section. Conical rings are 3 mm wide and are placed 48.5 mm apart. A circular pipe of diameter 48.5 mm and length 1950 mm was used as the geometry. A 3D geometry is created by using ANSYS workbench. Proximity and curvature sizing is used for meshing the geometry. It is meshed as shown in figures below. Total number of nodes was used 607,409 and total number of element used 166,0258. Fig 3. Mesh body sectional view. From grid independency we check the accuracy of the computational grid for calculating the Nusselt number and friction factor through the heat exchanger pipe. From the data we get to know that the number of elements varies between 15 loc and 20 loc depending on the value selected in sizing function of mesh. ANSYS Fluent 18.2 is selected for the numerical analysis by using finite volume method with simple algorithm. The flow is three-dimensional and incompressible, and quasi-steady flow condition. The momentum, energy, turbulent kinetic energy, and dissipation rate are discretized by using second-order upwind scheme. The residuals of continuity, momentum, K, and E equations for the convergence of the numerical computations are set to be less than 10⁻⁶ and 10⁻⁹ for the energy equation. 4 different turbulence models were employed for the numerical simulations: RNG KE, Standard KE, Realizable KE and SST-KW model. The KE-RNG turbulence model with enhanced wall treatment is selected for numerical simulation of the pipe with inserts. Under Materials tab in Fluent, the selection of material is done. Material selected is air. The properties of air is taken as follows. Hot air was used as the working fluid. The numerical studies were carried out with uniform velocity profile at the inlet of pipeline. The direction of the flow was defined normal to the boundary. Inlet velocity and temperature were specified. Turbulent intensity, I, and the hydraulic diameter, dH, were specified as 5% and 0.0485 m of turbulent, K, and outflow boundary condition was used at pressure outlet boundary. The wall of the pipe was assumed to be perfectly smooth with zero roughness height and stationary wall, no slip condition. Initial outlet gauge pressure was taken as 0 Pascal. Temperature was taken as 300 K. Constant heat flux of 1500/2 on the outer surface of the horizontal tube is applied. Velocity inlet boundary, inlet was taken for the pipe inlet section and the velocity values for the different Reynolds number are. Table 3. Velocity for different Reynolds number. Reynolds number. Each case must be initialized before the Fluent code begins iterating towards a converged solution. In this study, the option chosen for initialization was to compute from inlet zones. The number of iterations ranged between 800 to 12,000 depending on the case being run and how long it took to converge. Iterations were performed with the default under relaxation factors for all parameters. 6. Numerical analysis. 1. Grid dependency. Grid independence test. A solution refinement method is used. By using solution adaptive refinement, cells can be added where they are needed in the mesh, thus enabling the features of the flow field to be better resolved. When adaptation is used properly, the resulting mesh is optimal for the flow solution because the solution is used to determine where more cells are needed. In other words, computational resources are not wasted by inclusion of unnecessary cells. Furthermore, the effect of mesh refinement on the solution can be studied without completely regenerating the mesh. For grid independence test, a solution adaptive refinement method is used. By using solution adaptive refinement, cells can be added where they are needed in the mesh, thus enabling the features of the flow field to be better resolved. When adaptation is used properly, the resulting mesh is optimal for the flow solution because the solution is used to determine where more cells are needed. Meshing of the domain is done using ANSYS software. Computational domain was discretized using tetrahedral elements of different sizes. In order to resolve the flow near the wall accurately, prism layers were added. As it can referred in above, tabular representation grid independency test was conducted for CCR geometry. And all readings confer within standard range. 2. Validation of simple pipe. For numerical analysis, selection of appropriate model is required. By using the different ANSYS models, Nusselt number, nu, and friction factor, f, calculated and it further compared with the empirical value of nu and f, standard deviation range is 20%. 3. Numerical analysis of pipe fitted with circular ring inserts. 3.1. Numerical analysis for plain pipe. Numerical investigation of the heat exchangers tube fitted with circular ring inserts have been carried out. The cases were analyzed and pitch to diameter ratio was taken as unity. The numerical data is summarized in the following table. 5. Numerical analysis of ring inserts with conical circular geometry. 5.1. Analysis of the tubes with CCR with DR 0.6, 0.7, 0.8 respectively. 5.2 Nusselt number ratio calculation. 5.3 Friction factor ratio calculation. 5.4 Thermal performance factor, N. Rings were inserted in such a way that there is flow obstruction in the tube. The numerical data obtained is summarized in the following table. 8. Conclusion. 1. As per result, the nu and f both were increasing in the tube with insert as comparing with simple pipe. 2. As observed in result and discussion, Nusselt number increases with decrease in friction factor. 3. Thermal performance factor is maximum for 8 K Re CCR and minimum for 18 K Re CCR. 4. The maximum thermal performance factor of 1.2338 is found by the use of the CCR type ring inserts with 0.7 dr.